We have two independent companies, one with 2 plants and one with 3 plants. They serve entirely two different markets. Company 1 has 2 plants and serves 2 markets, and Company 2 has 3 plants and serves 3 markets. Entirely independent companies. We have cost of transportation from each origin to each destination, from each manufacturing plant to each distribution center. Cost per unit of product, per pallet, per container, per unit of product. We refer to them as CIJ, cost of transportation per unit of product from origin I to destination J. CIJ, CIJ, and then we have our decision variables, XIJ. How many units from this origin to this destination? These are our supplies, SI. These are our demand, DJ. We have N origin and M destination in general, but here we do have two entirely different systems, two entirely separate systems, and we want to find the optimal solution for each of them. Let's look at one of them. Two manufacturing plants and two distribution centers, two origins and two destinations, CIJ, XIJ. Cost table, this is cost table, and this is decision table. Come here, equal to summation . Equal to summation 1 and 2, and then copy to the right. This one, what has been sent out from origin 1, should be less than or equal to the capacity of origin 1. And this one, what has been sent out from origin 2, should be less than or equal to capacity. X11 plus X12 should be less than or equal to S1, and X21 plus X22 should be less than or equal to S2. Sometimes it is easier for us in future problems to bring S1 to the left-hand side and S2 to the left-hand side. So it would be minus S1. Here would be minus S2. And then we make the right-hand sides 0, less than or equal to 0. The same for demand. X11 plus X21, what has been gone from this origin to this destination and from this origin to this destination, should be equal to what this destination needs. The same for the other one. What has been sent from origin 1 to destination 2 and from origin 2 to destination 2 should be equal to the demand of destination 2. In linear programming formulations, if you can use less than or equal or greater than or equal instead of equal, do it, provided that you don't damage the logic of the problem. For example, here I can easily, instead of equal, write greater than or equal. I could write X11 plus X21. Instead of writing equal to the demand of destination 1, I can write greater than or equal. The same for destination 2. X12 plus X22. Instead of writing it equal to the demand for destination 2, I can write it greater than or equal. And the problem will never deliver more than D1 and D2. Why? Because the objective function of the problem is minimization of the total cost. And solver sees no logic to send more than 12 units to destination 1 and more than 19 units to destination 2 and increase the objective functions. As soon as we write greater than or equal, it will only send equal. Evaluation of less than or equal and greater than or equal constraints are easier in linear programming than equal constraints. Like the other part, instead of writing greater than D1 and greater than D2, we can bring D1 and D2 to the left-hand side, minus, and then write greater than or equal to 0 and greater than or equal to 0. We just move D1 and D2 from right-hand side to left-hand side. Note that total supply of the two origins of this firm is 35 and total demand is 31. So we can always find a feasible solution. Feasible solution is a solution which satisfies all constraints. I have already declared my constraints, and my objective function is sum product of these costs multiplied by these decision variables. In mathematical form, it's summation of Cij multiplied by Xij. In our problem, it is C11 X11 plus C12 X12 plus C21 X21 plus C22 X22, and that is what we want to minimize. Data solver. Oh, this may happen to you. It's like this question mark, solver. And then this is our objective function. We want to minimize it by changing our decision variables, which are these. Don't forget the blue and red part are two transportation problems for two different firms, each with some manufacturing plants and entirely separate markets. Add this one and this one by one, should be less than or equal to the capacities. Add this one and this one by one, should be greater than or equal. We don't need to put equal. Greater than or equal does the same thing of these two. Okay. Simplex, not nonlinear, but simplex, which is an effective approach to solve linear programs, developed by George B. Danzig at Stanford University during World War II. Solve. And this is the optimal solution for firm 1. We can repeat the same process for firm 2. Summation of these numbers should be less than or equal to the total capacity. Summation of these numbers should be equal to the total demand or greater than or equal to the total demand. And then solver, solve, and this is the optimal solution for red firm, and this was the optimal solution for blue firm, and summation of the two objective functions were $5,770. $1,000, $1 million, whatsoever. Could we find the optimal solution for these two entirely separate firms in one table? When we first introduced the problem, we said red firm operates here and blue firm operates here. Blue firm serve these two markets by these two plants, and red firm serve these three markets with these three plants. And for example, we cannot have a number here. We cannot have Xij greater than 0. It should be 0, and Xij should be equal to 0, because this firm has nothing with these markets, and this firm has nothing with these markets. My question is, can we create an integrated table, solve these two problems separately in one table? The answer is yes. All I need is to allocate very high costs. TheseCij's and theseCij's should be equal to a very big value such that solver will never go after some allocation over there. Of course, we can also say these Xij's are equal to 0 in this region, and these Xij's are equal to 0 in this region. This is more clear, but let me explain that one. We have two origins and two destinations related to each other, and three origins and three destinations related to each other. And the first set of origins cannot perform here, and the second set of origins cannot perform over there. They are two independent suppliers serving entirely separate markets. In order to solve this problem in one run, we can put big M's here, large values here. I have used this Excel function that if this number and this number are the same, write the corresponding transportation cost, but if they are different, a large number. Then I come here and I have equal to summation of everything. And then I want to go one step further, and I want to bring that 15 also to the left-hand side. Minus 15. Because it was supposed to be less than or equal to 15. Now if I bring this 15 to the left-hand side, it becomes negative 15, and this one will become 0. And then I copy it down. You may ask why I am doing this. Later on, for extension of this problem, I will add some additional random variables, and I cannot put them here on the right hand side. Variables cannot appear on the right hand side, and that is the main reason. The same for demands. This is demand of all markets, including those which this cannot serve. And then I also bring the negative of this one over there, and then I copy to the right. Data solver, not maximization, minimization, because we are dealing with cost. Minimization of this value. What is this value? The sum product of all cost elements by all decision variables, no matter if they can be greater than or equal to 0, like here and here, or they must be equal to 0, like here and here. And the formula for this one is here, and the formula for this one is here, and this is the objective function formula. Data solver objective function by changing these variables under the constraints of add this one and this one and this one and this one by one should be less than or equal to 0. Add this one and this one and this one and this one should be 1 by 1 greater than or equal to 0. Okay. All decision variables need to be greater than or equal to 0. Simplex sum. And this is what we found as summation of the objective function of the two problems when we solve them separately. 5770, and this is aggregated problem. Now let's go one step further and suppose these two companies have merged. And now they can serve everywhere. We remove this one and we just copy the cost function. Constraints are exactly the same. Let's remove these decision variables. It doesn't matter, it can stay on the other side. When we bring these values to the left, usually we want to multiply them by decision variables so they cannot be on the right hand side, and then they should go to the left hand side. But for the time being, they are just numbers. I can keep them there. Data solver, minimize this objective function by changing these decision variables. And by having this one and this one and this one by one, less than or equal to this one and this one and this one, add these values greater than or equal to these values. Okay, all decision variables to be greater than or equal to 0. Solve. Okay, find the optimal solution by merging these two companies, by allowing this origin to also serve these destinations, and by allowing these origins to also serve these destinations, we were able to bring the objective function value to 5545, which is 225 below what was before merging these two companies and allow them to operate in each other's region. They really do not need to be financially merged. They just may collaborate with each other's, and they can reduce their cost by 225 just by collaboration. Thank you very much. I will continue on capacitated transportation problem in my next lecture.